So welcome everybody. This is a seminar tutorial of the Restart tutorials on telecommunication series. We have the pleasure to have with us Francesco Linsalata. Francesco is assistant professor here at Politecnico di Milano and will be delivering a tutorial on integrating connected and autonomous vehicles into the 6G era. Francesco has experience in this field, in particular in his research. So I'm sure that the presentation will be very interesting. I kindly ask you to keep your questions for the end so that we can record the tutorial until the end, and then we will stop the recording and you will be able to ask questions. So Francesco, please, the floor is yours.
Thank you, Antonio, and thank you all of you to be here. Today, as Antonio told you, I will deliver a speech on what will be one of the killer application of 6G, so connected and autonomous vehicle. So first of all, before starting, let me introduce myself. I did both my PhD and master in telecommunication at Politecnico di Milano, where I'm currently a researcher or assistant professor. I'm involved in a couple of academic activity. I'm teaching the communication system course and also the course of fundamental of signal transmission. My research activity mainly focus on currently on Restart project. I am within the structural project 6G YNet. I'm also involved in a different research activity with industry, like in the joint lab within Huawei and Politecnico di Milano, and also currently with a company for UAV localization. My research interest is mostly about physical layer, so I am a physical layer guy. But I have also some interesting on the next generation wireless network from the architectural point of view. First, before starting, I would like to ask all the people that you see listed here. This is mainly all the people that allows me to have a lot of slides on this topic. So I really have to thank all of them. And if I forgot someone, I will for sure add it in the rest of the presentation. So as usual, we do in research, when we start a paper or a research talk like this one, we start with the motivation. So the vision that we have in our, let's say, research group, but I think the vision that all of us has on future cellular network is that they are expected to be extremely heterogeneous in terms of involved wireless technology. Among them, we have vehicle to everything technology. We will have different set of communication services that support different application and use case with different requirement. And for this reason, we need to have a high and pervasive vertical orchestration of this. So each technology has its own strength, its own weakness. So, and here today, I will try to show you which are the, let's say, the pros and cons and the good point and weak point of V2X technology. What we have as a telecommunication researcher is experience on each technology, and we are here to, let's say, to share this experience. And what we are working on is the possibility to make this technology better by developing new algorithm, new protocol, and new architecture that allows to make a network more, let's say, intelligent and more ready for this new application. So when I started my PhD, let's say 6 years ago, now I am a researcher, I finished my PhD, the first question I posed to myself was the one that I usually use to start this presentation. Why cars should make use of a communication interface? So why we should have a communication interface on board of a car? If you think to if you think to the possibility to increase the autonomous level of a car, so passing from level one, where the human driver, where the pilot does everything, up to level five, where there is no more interaction of the human, so the ADA system can perform all the driving tasks in all the circumstances. This means that we need to increase the number of sensors on board. So we need to increase the number of LiDAR, number of radar, and number of camera on board of the vehicle to to let it to be more autonomous. And this means increased cost. And so the main reason behind the possibility to have a communication interface on board on a vehicle is to reduce this cost, in the sense that instead of increasing the number of sensors on board, we can use the communication interface on board of the vehicle to rely on the sensors that are on board of the vehicle that are around us. In this way, we can create a common perception of the environment that not only reduce the cost of the vehicle itself, because we are reducing the number of sensors, but also increase safety because by having a common perception of what is happening around, we can also, let's say, increase the possibility to take common decision to avoid accident and to maximize the cooperative perception of the environment. So the cooperative safety of the environment. So after I provided you the motivation, I would like to start with an overview on vehicular network. And as I always do in this type of presentation, I really like to start with the history behind. In this slide, I reported three different timelines. So in the top of the slide, you see a red line that mostly is the history of telecommunication. I think all of us know it. So starting from the Maxwell equation up to the 4G and then moving to 6G. In the bottom part of the slide, you have a green line that identify the historical evolution of the car manufacturing. So starting from the first example, the first engine example, passing towards the diesel engine, arriving to the first case in which we have a sensor on board on a car, an Honda as a GPS, had a GPS mounted on the vehicle. Then at the beginning of this century, we have the first example of autonomous vehicle provided by Google. And some years ago, in 2020, European Union start to, let's say, push toward autonomous vehicle by introducing new regulation for autonomous level number 3. In the middle, I report the interaction between these two, let's say, line between these two industry. And as you can see, they never interact each other up to 1970, when we have the first electronic road guidance system, where there was the first radio frequency interface on board of a vehicle. The first protocol, the first standard that has been defined for this type of communication was the dedicated short-range communication. It actually was born for a wide application, among of them also communication between two vehicles, two cars. And the first real, let's say, network protocol for vehicular communication was born in this century, so at the beginning of 2000, where we have the first concept of vehicular ad hoc networks. Then we have the evolution of this. It was also during, let's say it started, we have also the first example actually was based on Wi-Fi. And then we also have the first V2X, vehicular ad hoc network, based on cellular communication, first with 4G and then with 5G. And nowadays, these two lines try to merge together because, as I told you at the beginning of this presentation, connected and autonomous vehicle will be one of the killer application of 6G. Still a bit of history. As you see in this slide, I reported the first patent on V2X system was a patent of German group in 1926, and in this patent mainly they delivered the first example of a radio system used to allows communication between two vehicles for mainly warning purposes. So we mostly have two type of communication mode in this type of V2X or let's say vehicular network. The first one is direct communication. So direct communication means communication between vehicle, so V2V, or vehicle to infrastructure, V2I, or vehicle to pedestrian. When we have a set of V2V communication that are, let's say, cooperating together, we can create what is generally called a VANET. This type of direct communication, they are mainly short-range communication, so lower than 1 kilometer communication with dedicated bandwidth at FR1 or FR2, also known as millimeter wave bandwidth. And this type of communication mode is mostly used for latency critical services, like the one that you can see here. So services that are, let's say, mostly let's say have a high constraint on the delay. The second type of communication mode that we have is network communication, and they are mostly for long range long range application. And here, as you can see, mostly is a vehicle to network, so vehicles that directly communicate with the edge and the core of the network passing through a base station. And let's say for this type of communication, the application are mainly latency tolerant services where telematics, infotainment, and informational safety are the most present ones. So let's say there are two different communication mode with different requirement and thus different application. From the point of view of the communication technology, we have mainly two type of communication technology. As I told you, the first example was Wi-Fi based, while nowadays, let's say, cellular V2X is the one that seems to be the most promising. So just some information about the two. So Wi-Fi based vehicular communication is also referred as a dedicated short range communication system, and is based on 802.11, actually 11p. And the frequency, let's say, mostly operate at FR1, so sub 6 gigahertz, with a bandwidth of 10 megahertz. So the bandwidth is quite limited. It is based on the signal that is transmitted is based on classical Wi-Fi waveform, so orthogonal frequency division multiplexing, with let's say, transmission rate that is quite limited, since as I told you, the bandwidth itself is limited. And the good point of this Wi-Fi based vehicular technology is that is mostly for low latency application, and it suffer a lot the distance, in the sense that it's mainly for us all Wi-Fi system for short range communication. So as you can see here, it accepts a maximum range of 500 meter in direct line of sight, so when there is a direct communication between the two vehicles. From the other side, we have cellular V2X, and as I told you, there was a first release based on 4G LTE, and nowadays people are mostly using new radio V2X based on 5G. So LTE V2X, let's say, as an improvement in terms of transmission rate with respect to Wi-Fi. We can arrive up to 1 gigabit. Also, the range is extended, so it has a better scalability and management of the interference, still based on FDM. And the main limitation of 4G based V2X is that LTE has some frequency constraints, and let's say there are no specific solution for mitigating the Doppler effect that are present at the high speed of the vehicle. On the other part, we have 5G V2X, so new radio V2X, that actually is not born as a, let's say, opposite solution with respect to 4G, but is totally complementary to 4G. So it's a sort of evolution, but coexistence between the two technology can be allowed. And the new point is that it support two type of carrier frequency. It can work both at FR1 and FR2 millimeter wave with a bandwidth that in the first case arrive to up to 100 gigahertz. In the second case, we arrive up to 400 gigahertz. So it means a lot of bandwidth, and this means, as you can imagine, a higher flexibility, extreme data rate, and mostly overcome the limitation of both Wi-Fi base and 4G V2X system. The main challenge of 5G V2X is mostly related to, let's say, the new technology that are present in 5G. So I'm referring to let's say massive antenna system with MIMO and beamforming management. So there are let's say new technology, new approach that are present in 5G, but these need to be studied to, let's say, to be also implemented in vehicular communication. And for this reason, one of the, let's say, main problem of 5G based V2X is that we need at least it's a problem for us, but for us it's a good point because we are researchers, we need to do that. There is the need of doing a simulation to understand what is happening when we use this new 5G technology in a vehicular environment, with the scope of understanding their behavior in this environment and try to optimize them to make the, let's say, to make a real world deployment of this 5G V2X technology. So let's say in a word, we need to simulate it to understand if there is the possibility to use massive MIMO, high frequency, and higher bandwidth also in vehicular environment. From the system architecture point of view, as you can see, it's mostly the same architecture that we have in a classical 5G network. So we have a core, we have an edge, and we have a RAN. So the core consists of several network functions, as in mostly all the 5G, as also is present in 5G network, while the RAN architecture is, let's say, still a mix of 4G and 5G. And from the point of view of the protocol stack, as you can see here, we have mostly the same protocol stack of a classical network, with the physical layer, the network layer, and the application layer. With let's say, all of them are specific based on the Wi-Fi, 4G, and 5G, but from the overall point of view, it's mostly the same from the, let's say, the division point of view. So as you can see, as I told you, there are mostly two type of communication technology that allows to have this V2X system. One is Wi-Fi based, and the other one is cellular based, or 4G and 5G. And for some people, this is the main reason for which most makers are hesitant to launch this V2X technology in the car. But if you do some research around, you can see that actually most of them have already chosen to adopt one technology. Here I reported some examples or of different automakers that car makers, sorry, that are currently using one or the other technology. And one of the main problem is on V2X is that we have a very, very low penetration rate. In 2021, it was expected to have 100% of penetration rate of V2X technology, but the penetration rate with numbers at the end was only 5%. So we have 1.5 billion of cars circulating, or only 80 million had V2X technology. And in Europe, we have only two types of cars that are equipped with V2X technology. So low penetration rate is an open issue. However, the number are nowadays are better. Let's say we have an increase on the penetration rate, and they are expected to improve up to the 2033, and this is also, let's say, anticipated by the fact that the government is investing, is pushing, is putting money on V2X technology, also from the point of view of the road infrastructure. Also in Italy, we have, especially in Milan and Turin, we have a lot of investment to make the highway and the road ready from the infrastructure point of view, ready to support this V2X technology. So in this slide is let's say, so until now I give you an overview. I also speak about what is the industrial perspective on V2X. Now I give you what is the research perspective on V2X. And I took inspiration from a talk that one of our colleagues in Bologna did, where mostly divided the research on V2X in 3 days. So the first day is something that is ready and deployable. Is the day in which the vehicle is capable to share where it is. And this is something on which we did research, we did prototype, and we are ready to have this. Actually, a lot of cars that are now on the market as this type of, option, this type of technology. Day two is the possibility to share where what they see. So in the idea, in the scope of creating a collective perception. And on this we did research. So we are ready from the research point of view, also from the point of view of the standard. And now people in industry start to apply the concept we found in the research. And day three is that where now research is looking to, so where people working also in restart program is looking, is the possibility to have coordinated maneuvers. So all the vehicles that are connected and coordinating try to have a common they have a common perception of an environment, and so also they try to have a common maneuvering, trying to increase, as I told you, as a motivation, the safety of the environment. And on this research, we are doing research, we are trying to understand the possibility to have this type of system. We have, mostly to make this possible, we have different type of messages that are standardized among vehicle. Here I just report some of them. We have a vulnerable road user. Then we have collective perception messages where they, as I told you, exchange this sensor data, and also cooperative awareness messages where they exchange. There are messages that are used to exchange the presence of specific condition for which other vehicles should be aware. And the last type of messages that allows to have, let's say, the maneuver coordination is the maneuver coordination messages, and this is messages that are standard that have been recently standardized. From the point of view of the standard, this is a very high level overview. I don't want to go into detail of what happened in all the different releases of V2X technology. I just want to keep your attention on the requirements of the V2X system. As you can see, the latency requirements are very, very strict. We have a latency requirement of 3 milliseconds up to 100 milliseconds, and also the reliability requirement is a very hard to satisfy requirement, and this is something on which we need to work, and we need to optimize the network to satisfy this type of requirements. Yeah, what will be in the next release? So now release 18 is available, and in the standard they are speaking about what will be the next release. And I did some search around, and these are the main keywords that I found. I just want to maybe stress a bit the possibility to have a better spectrum allocation and management for V2X system, the possibility still to improve the communication reliability with higher data rate, and the possibility also to improve the data privacy and user consent. That is a very delicate and key aspect on this type of system. And there are a lot of expert people that are working on this last point to make it possible also in V2X environment. So after this, let's say, overview, I will still, let's say, continuous I will still keep going this presentation based on, let's say, what I learned in my experience, like a PhD first, and then like a researcher. And after I found the motivation behind the V2X system, what I try to do is understand how to simulate a V2X system. So I would like to start with, since I am a physical layer guy, to start on how we can simulate a V2X channel model, and what is the simulation methodology I understood could be a good way to simulate a vehicular environment. What you mainly need is a framework of different different tool and different let's say simulator. And the first thing that generally you need to have is detailed 2D maps of the environment that you would like to simulate, and there are a lot of software that allows you to have this information. For example, OpenStreetMap, a model of vehicles, of the mesh of the vehicle, and on these there are different software, like for example Carla. And the most important aspect that you need to have a good simulation of a vehicular environment, a vehicular network, is a mobility simulator. And on this, the literature offer the possibility to use Sumo, that is a simulation of urban mobility, and it can be easily interfaced with OpenStreetMap data. And these two, integration of, let's say, these three aspects, so the environment, the scenario, the vehicle meshes, and the mobility simulator, give us a quite good automotive simulator, on top of which we can then run a ray tracer or a geometric-based channel simulator to retrieve information regarding to the channel. And when you combine let's say, yes, this is an example of all what I told you before. So you need to have a blender model, so image of the scenario where you would like to simulate your vehicular environment. Here, this is our Polemy campus. Here, this is an example of simplified vehicle models, the mesh of the vehicle that have been extracted by Carla simulator. And in this case, here I reported this. Mesh on in our scenario by having both parked vehicle and moving vehicle, where the mobility, as I told you, is modeled by using Sumo. And this is, let's say, an output after you run a retracer or a a geometric channel simulator, where you have, in this case, you have a transmitter that is a base station and a vehicle that moves. And as you can see, by moving the vehicle, the multipath generated by the transmission by the base station towards the vehicle change, because it start to interact with the different element present in this environment. And this is a way, let's say, to simulate a channel model. As I told you, a key aspect here is for sure the retracer that you would like to use. On this, I had some experience on different retracers that I reported here. All of them are compatible with vehicular environment. All of them allows you to simulate a scenario like the one I showed you before. Most of them are proprietary software, but in all, I think most of the university in Italy, but also in Europe, has some licensing to allow us to allow the researchers to use this software. Only two of them are open source: is NVIDIA Siona Retracer and GMB Square, that was developed by a researcher in Huawei Munich. So from the point of view of the channel, I try to summarize in a couple of slides how you can simulate a vehicular environment. While from the point of view of the network model and how to simulate let's say a full stack VANET, there are different different tool available, different software. One of them is an open source framework that is based on Network Simulator 3 and has been developed by our colleague at Politecnico di Torino. It's called MS VANET, and is a very quite complete software that allows you to simulate all the standard we discussed before, and allows you to, let's say, have to implement different type of messages. Among of them, you have like cooperative awareness messages or other type of messages we discussed before. And it's quite flexible and scalable, in the sense that the physical layer and the MAC layer are totally programmable, so you can modify them. And yeah, there are also different use cases where they demonstrate with simple application and key performance results. So they allows you to test different condition, and they already make the, say, they have some KPI, KVI that are already present in the simulator itself. Another software that allows still for a full stack simulation is Millicar, that actually is been developed by another Italian university, is Padova, University of Padova, and is the first NS3 module for V2V millimeter wave networks, and I think also is the first simulators that allows to have a geometric based channel model within NS3 for millimeter wave networks. It's open source as all NS3 based simulator, and enables research and comparison of different design option. And as I told you, especially for 5G, millimeter wave and beam-based communication is a very good point. And as I told you, is an end-to-end simulator, so it allows to simulate from the physical layer up to the application layer, and this is specific for V2V and millimeter wave. Then
Let's go 20 minutes.
Okay, then I move to the emulation tools, where you have, let's say, only one, let's say, emulator available. That is the one that is also quite famous here in Italy, because again, it's been developed by Politecnico di Torino. And this software is called Oscar and is an open source framework that allows you to implement an Etsy stack for embedded hardware devices. So it allows you to do some hardware test for different type of ETS services, and it is designed to be easily port the code of application from simulation to real world. So it is, let's say, designed in such a way it can be integrated with MS Bonnet. And this is an example of Oscar framework, of Oscar setup of an experiment we did in collaboration with Politecnico di Torino. Here I have some slide. I will go very fast on this slide, where I just give you which were the main challenge and solution I focused during my research on V2X communication. As I told you, the new technology of 5G are putting some challenge for V2X application. Mostly I'm referring to MIMO, so spatial synchronization in dynamic environment is a crucial aspect, and the fact that we need to optimize the network connectivity, especially when we work at high frequency like millimeter wave, because the path loss is an important problem. So let's say the main two questions I try to answer in my research is when we rely only on the communication interface, where I have to look to find another connected vehicle, and who is the best communication counterpart to exchange data. So how we can avoid a situation like the one that you see here, when we have an obstruction of the link, and how I can design a smart solution like the one that you see here on the right to keep my V2X link safe. Well, so one of the challenge I try to face, but here I will be very fast, is the possibility to improve the spatial synchronization between two vehicles. So the idea is how two vehicles can understand which is the best direction to communicate by using a MIMO system. From the standard point of view, the current 5G radio is based on exhaustive search, so it means they test all the possible beam pair until they found the optimal spatial direction. And as you can see, as you can imagine, in vehicular environment is not a good solution. And another one is a position-based approach, where vehicle exchange GPS to, let's say, improve this spatial synchronization. Even if it is very good, it's very simple also, it is not always possible to have GPS information at the communication interface. So the solution we propose is a very simple solution, where we exploit the fact that in a vehicular environment, due to the road topology, due to the, let's say, environment itself, only some communication direction are possible. So we can prioritize some beam. This can be learned by a traffic-based approach, in the sense that we learn which are the most probable communication direction by exploiting a training procedure, or directly by the map. So we can apply some image processing. I don't want to give you the detail on the map itself. So based maybe on the vehicle planned path, to understand which are the most probable communication direction. So we can extract some PDF of the angle of arrival, angle of departure, and based on this, we can, let's say, maximize and minimize actually the training time, so the time that is required to align the two beam. And as you can see, the result that we got is quite interesting, especially because we for sure we do better than 5G new radio, but we are capable to achieve the position-based approach without requiring the position of the other vehicle. Another possible solution here, I will be very fast to let's say improve this spatial synchronization is the possibility to rely on a radar on the base station, because as we know from Isaac, the radar mounted to the base station provides some position information about a user, in this case about a vehicle, and this position information can be used to optimize the beam search. So from the angle radar image, we can, let's say, obtain the information regarding to the possible direction of arrival and direction of departure of our vehicle. And we can use this information, let's say, to maximize, to minimize the code book, so the possible spatial direction where we have to look to let's say to establish a communication. We did some experiment based on this idea, and we also model what is, let's say, the image that a car is, how the car is perceived by a radar, and then we use this information we earn to do some simulation and obtaining, as you can see, when we use a radar, even with not very high accurate precision, the radar accuracy mostly depends on the bandwidth of the radar. We are able to obtain, let's say, to minimize the training time quite a lot with respect to classical approach. As I told you, one of the main reasons for which we should have a communication interface on board of a car is to exchange sensor data, because sensor data, when they are, let's say, well processed and they are available on a vehicle, they can be used also to detect pedestrian and obstacle. So this is an example of some experiments that the radar group at Politecnico di Milano did. And however, to have this perception of environment, we need to develop some algorithm that allows to maximize the network connectivity and the link selection. So here the goal, as I told you at the beginning, is to avoid condition like this where the link is obstructed, and maximize, let's say, the possibility to rely on other vehicle to keep the condition, keep on the link condition. And on this we develop, and also in this case some possible let's say algorithm based on the line of sight prediction. So based on the geometry of the environment, based on the scenario, we can in some way predict the line of sight condition among the vehicle, and based on this prediction we can also, let's say, have an estimate of what will be the signal to noise ratio, so the link condition. We can model the PDF of the signal to noise ratio, and then we can exploit this a priori information on the SNR to define some optimization algorithm to, let's say, prone a relay assignment scheme, and this can be then, let's say, as we did in our research, can be solved both in a centralized and a decentralized manner. So by using a base station or directly among vehicles. So here I can skip all this concept, but I just want to show you that when you let's say use this type of approach, when you rely on the possibility to have a relay, you can increase the network connectivity up to the upper case in which all the links are available, just by optimizing, just by let's say employing this a priori information of the environment and PDF of the signal to noise ratio of the environment. Yeah, I think I can skip this part where I think there will be a talk on the possibility to use also ORAN in a vehicular environment. This is a recent architecture we propose where we, let's say, we rely on the main idea of ORAN, of programmability and and control capabilities within a vehicular environment. And this is a work we did where we propose the architecture you can see here. I think we have been the first one speaking about ORAN in a vehicular environment. We did some tests by using NS3 approach. So we use one of the simulator I discussed before with you, and these are some results in different, let's say, V2X application, different V2X use cases, where we compare the proposed MobiOran approach, where an X-Hub has been developed to mitigate the problem, the issues of different use case of a vehicular environment, compared to a 3GPP standard approach. And as you can see now, I don't want to go too much into detail, but as you can see from all these graphs, in most of the case, the ORAN-based approach is capable to improve the KPI of the overall network itself from the point of view of the spatial synchronization, the resource allocation, or the network connectivity management. Last part of this presentation is about let's say a topic that nowadays I think one of the most interesting one, at least from my point of view, or also let's say one of the main topic present nowadays in the research paper is network digital twin. And network digital twin in a vehicular environment, I think, is well suited because, as I told you, vehicular network, at least for me, were born because they need to exchange data. And when we have a lot of data, we can rely on this data to create what is generally called a digital twin of the environment. So we can rely on these information that are present in this information that is exchanged by the vehicle with different type of sensor data to create accurate digital mirror of the physical model. And then this digital twin can be used to control the real world. And as you can imagine, this should be updated very fast to have a good control of a vehicular environment where everything is also changing quite fast with respect to a standard communication and network use case. From this point of view, we are currently working on this. This is an example of the digital twin that we developed at the Politecnico di Milano. Is the digital twin of our high frequency campus, where mostly are present all the ingredients I told you at the beginning to create a digital twin of let's say of the physical layer of our vehicular network. So we have the 3D detailed map, and with the vehicle mesh that have been imported, and is moved within this environment, and then we run a ray tracing simulation to obtain a digital twin of the electromagnetic propagation of this environment. The last slide is about a recent simulator we are developing on this concept of digital twin. This simulator, I think, is the first time we present this. It's called VANET Twin, and is an integration of what you saw here with the MS VANET simulator. So we integrate our expertise on the physical layer and the possibility to have a digital twin of the physical layer of a vehicular network with the MS VANET tool that was developed by Politecnico di Torino. And we propose this first full stack and multi-stack V2X network digital twin. Is one of I think one of the most important output of Restart program, and where this simulator allows also, as I told you, for the possibility to, thanks to the use of ray tracing on the loop, the possibility to model and simulate coexistence scenario. So trying to understand what is the effect of having different radio access technology in the same spectrum. And let's say the most simple idea is the possibility to use a ray tracer as again in the loop, where this ray tracer is capable to communicate with the higher layer of MS VANET in a dedicated way by using a UDP socket. And all the detail will be, I think, quite soon available in a research paper we are going to publish. So I think this concludes my presentation. I have been quite fast in the last part, but if you have some question and you would like to know more on this, you can contact me on the email you see here in the bottom.